Okay, well, good morning, everyone. My name's Aaron Davis, and I'll be giving a series of fairly quick talks today dealing with, I guess, the broad topic of what we think the current state of water quality science and catchment water quality is in the Great Barrier Reef environment. And I certainly need to point out early on in the piece that this is far from a standalone effort on my part, and it's really probably the culmination of decades of research effort from hundreds of different scientists who've done fantastic work, and I certainly, unfortunately, don't have time to appropriately acknowledge all of their contributions. Just to provide a quick overview of how the talks will work today, I'll be working really quickly in a rapid-fire way through what we know about water quality and its impacts at the marine and probably up into the catchment scales. So we've got a picture here, probably most people are familiar with, of the Great Barrier Reef catchment continuum from the paddock to the marine environment. I'll be working and talking mainly in this space here in red. So I'll be looking at three water quality parameters that we're currently worried about: sediments, nutrients, and pesticides, and looking at them in separate presentations. And I'll be defining, in some ways, the challenges or problems that we're dealing with in the catchment and marine environment. Kevin McCosker will be following each of my presentations with a focus on management practices at this scale here. So what you probably can call the paddock scale in the blue box here. So I'll be defining the problems, and Kevin will then be following up with a presentation about the solutions in terms of land management practices. So the first topic I'll be dealing with today is the role of sedimentation in Great Barrier Reef water quality. But before I launch into that, I probably need to give a little bit of a definition of sediment. So sediment's basically defined as any particle that's greater than 1 micron or about a half a micron in size, depending on the definition. And that can include things like inorganic soil particles, clay particles. It can also include things like some particulate forms of organic material. But it's really important to realise that sediment size is a really important influence on the ultimate environmental fate and the ecological impact of sediment once it gets out in the environment. And when we're talking about the ecological impacts of sediment, we're really concerned about two probably main mechanisms. One being direct sedimentation, which is basically just a smothering or burial, particularly of sort of aquatic or bottom benthic habitats. And the other major effect is on sort of long-term or even short-term changes in reduced water clarity or how far light penetrates into the water column. So where's the sediment in the Great Barrier Reef marine environment and river systems coming from? And how is it generated? Our best estimates at the moment suggest that there's been a 5-fold increase in annual fine sediment loads that are delivered to the Great Barrier Reef marine environment. And grazing land by far contributes the largest proportion of this sediment and particulate nutrients to the marine systems. And that's mainly in the form of channel erosion, so gully and stream bank erosion, and things like scolds or hill slope erosion are also fairly significant contributors, particularly in dry years. But gullies alone, we think, contributes around 40% of the fine sediment to the Great Barrier Reef, and that just comes from around 0.1% of the grazing land. But it's probably also important to point out that while that grazing land dominates that picture simply by virtue in many ways of how much land it actually covers, hundreds of thousands of hectares. Some of the more intensive cultivated agricultural systems, their sediment yields on a tonnes of sediment per hectare basis loss can actually be higher than grazing lands in some cases. So when we're talking about things like bananas, sugarcane, and some broadacre cropping, but it just sort of really depends on the context of the particular management practices at play there, the slope of the environment and other things like that. Sugarcane is actually a really interesting, I think, good news story for sediment management in the Great Barrier Reef context. Decades ago, they were probably losing lots and lots of topsoil and sediment, but the sort of widespread adoption across much of the industry of green cane trash blanketing sort of put a really big hole in that, and it's kind of one of the, I think, the really good news stories when it comes to industries and natural resource management responses. I'm going to look now at a few key questions fairly quickly. So does river discharge and the associated sediments reach vulnerable marine ecosystems? And what are those effects, if any, out in the marine environment? And what are the sort of parts or areas of the Great Barrier Reef that we think are most influenced by sedimentation? And it's a big topic, and I'll just mainly limit what I'll be talking about today to a case study focusing on the Burdekin River catchment. And there's a number of reasons for that. It's been identified as a real hotspot for sediment generation. There's been decades of lots of really high quality research coming out of the Burdekin River catchment along its length and out into the marine environment. So it's a really appropriate case study to talk about impacts of sediment on the marine ecosystem. Okay, so to jump straight into the Burdekin River sediment story, up here I've got a satellite image of a flood plume event that occurred in the early stages of last year, early 2019, from what was probably just a moderate-sized flood event occurring in the Burdekin catchment. And hopefully towards the bottom right of that slide, you can make out Old Reef. It's a mid-shelf reef that probably located 70 or 80 kilometres from the mouth of the Burdekin River catchment. And you can sort of make out here a fairly obvious sediment plume extending in an easterly direction, basically from the mouth of the Burdekin catchment, heading towards Old Reef. So if we jump ahead to the next day's satellite image, you can hopefully clearly make out here that that sediment plume is now basically obscured or covered Old Reef, and it's still extending in a roughly easterly direction from the mid towards the outer shelf reef. And it's probably important to point out, however, that plumes that behave in this way from the mouth of the Burdekin aren't a highly frequent event. They probably occur once in about every 10 years. And it's usually a bit more common because of the prevailing near-shore currents and wind direction for any plumes from the Burdekin that tend to happen maybe once every 2 or 3 years to extend in a more northwesterly direction up the coast. And here's just another few images of different stages of that flood plume, and you can see the sediment progressively covering different parts of the mid-shelf reef ecosystem at Old Reef. So we've got a nice, some nice visual images here of the water quality occurring at different parts of that plume as it moves through from the Burdekin River mouth during that particular event we're just discussing. And you can see here on the slide, the plume is a lot of sediment, very dirty water, up around 590 milligrams per litre near the mouth of the system, but it tends to drop away fairly rapidly within about 10 kilometres of the coastline. But you can still see there that we're still picking up appreciable levels of sediment as far up the coast as the Magnetic Island reef ecosystems and also the Palm Island group. Just a nice visual image of how quickly some of the material drops out of those plumes. So I'm just going to talk here very briefly about the sediment dynamics within these plumes and how we think that they work with the different, particularly the different sizes of sediment and their area of influence. So we think currently that most of the coarser sediment tends to fall out here in this sort of blue circled zone here within 10 to 20 kilometres of the river mouth. Most of the sort of coarser sediment falls out in this area and doesn't tend to move much beyond that. The finer sediment tends to move much further, and there's a picture here of it's a microphotograph of a sediment flock, we call it, collected from these Burdekin River plumes, showing the different components of the flock. It's probably a bit hard to make out if you don't know what you're looking at, but most of the mineral sediment here is really quite small in these flocks, so usually less than 20 microns, but they're also surrounded by this mucousy organic rich material, which is made up of bacteria, microalgae, all sorts of different things, and probably generated in part also by nutrients entrained in the plume. But these sort of this finer sediment travels much further from the river mouth, hundreds of kilometres, and it can eventually settle out, but it tends to settle out as this sort of probably light, fluffy layer on the habitat on the bottom of the ecosystem that's fairly easily resuspended by wave and tidal action. And we've actually got some nice data showing the impacts of these flood plumes through time from the Burdekin River catchment. I don't want to spend too much time on this, but basically we've got data showing that during dry years with small Burdekin River discharges and flood plumes, like at the scale of what you'd see here, Light penetration out in the GBR marine environment usually extends well below 10 metres into the water. Very different story in wet years when you have big events and big flood plumes come out of the mouth of the Burdekin system. The depth of light penetration, or photic depth, it's substantially reduced, often well below 10 metres for several months of the year. And if you're a coral or seagrass sort of in water deeper than that 10 metres, you're probably really going to struggle to get the sunlight that's really a critical part of photosynthesis and your survival. And we've actually got some interesting ecological data to document the environmental impacts of these plumes on the receiving environments of the Great Barrier Reef marine habitats. And I've got a series of maps up here from a study showing changes in seagrass extent from 2007 to 2011 in Cleveland Bay, which is sort of a key receiving area for flood plumes from the Burdekin. So in 2007, 2008, 2009, a lot of big wet seasons, big Burdekin flood plumes that moved up through that area. And you can see in those graphs from some fairly drastic reductions in the area, or contractions in the area of seagrass in Cleveland Bay. And that was probably due to direct plume impacts, but also from subsequent resuspension events through the dry season, where that fine sediment got resuspended up into the water column and affected water clarity. And in 2011, the system has almost got wiped out entirely by the impacts of Cyclone Yasi. But subsequent to this, they have bounced back to a certain extent. So there is a degree of resilience in these ecosystems. So just in terms of a really quick summary, in terms of direct sedimentation, the main influences in the marine environment we think are on areas that are quite close to the river mouth, usually within 10 or 20 kilometres. But it's that really fine-grained suspended sediment, that less than 20 micron fraction, that really gets entrained in those sort of organic-rich flocks in flood plumes. They can travel much greater distances and have much greater area of impact, and particularly through changes on water clarity and light penetration. And these are the fine-grained material is really what we need to manage better in the GBR.